All right, let's get this started. Welcome back, everyone. Seems to be working again. Finally, the keynote of ISMM. This time around, we had to shuffle things a bit to accommodate Steve on the other side of the planet. And so it's a pleasure to welcome Steve Blackburn here today at ISMM. For those of you who don't know, Steve is a research scientist at Google Brain and also a professor at ANU. His main focus, I would say, is PL implementations and GC, but really looking through the list of publications, it's anything memory management at this point, OS, virtual machine architecture, compilers. So I'm very much inclined to say it's computers in general. In that spirit, he also has two papers on GC at PLDI this year, so I'm definitely going to check out those. What's maybe a little less known is that Steve was also a visiting researcher working on the V8 JavaScript virtual machine recently. I mean, it's quite some time ago, but I'm still saying recently. And you know, V8 has a very steep learning curve, and it was very inspiring for me to see how he would still get his hands dirty in writing actual code, measuring machine assumptions, and quite unsurprisingly, often coming out ahead with new findings. So I think that was very inspiring to see. And so I'm really curious, and I'm excited about the topic of this talk actually. And I'm really curious whether we will learn about a few assumptions that maybe we should reconsider at this point. And so please go ahead, Steve.
Great, thank you, Michael. I hope everyone can hear me just fine. Welcome to ISMM, one of my favorite venues. And I'll just say that that visit to Michael's team was a long time ago. In fact, it was February 2020 that I left, so an entire pandemic ago. And it was absolutely amazing. And in fact, of course, contributed to me deciding to move to Google. I had a great time there. So thank you, and thank you for that very generous opening. Yeah, so the title of this talk is that we live in interesting times. I'm going to say a bit more about that in just a moment. But it is a real honor to be here, and I'm really sorry that I couldn't be there in person. I would absolutely love to be there. I can see people on the gather screen virtually. There's a great crowd of people there, friends and faces who I know. And I'm sure there's a room with a bunch of people there who I would be very keen to catch up with after this, if I could. And thank you for accommodating my time. It's 9 a.m. here in Sydney, and I feel very fortunate that people adjusted the schedule to accommodate that. So let's dive in. I want to start the talk with a little reminder. I mean, Michael's already pointed out that I'm coming to you from Sydney, but also this is a nice tradition. I think it's a nice tradition that we have in Australia. When you give a talk, you acknowledge the traditional owners of the land you're on, because Australia, of course, was colonized about 200 years ago, and in fact, the colonizing ships arrived just about a mile from where I am sitting right now. And I'm on Gudgegal land. The people who lived here never ceded the land. They're the traditional owners of the land. And we often in Australia start our talks by giving an acknowledgement of that. But also, I use this picture when I give my intro CS classes to remind my budding technologist students that there's a lot of history in front of them. In this talk, I'm going to talk about 60 years of memory management history, but there's a greater human history that comes before us. And it's often, I think, humbling sometimes to put ourselves in the context of that broader human history. And in this case, this is a rock art that's not very far from my house in Canberra. And it's dated tens of thousands of years old, which helps us keep ourselves in context. So, may you live in interesting times. The title of the talk was Interesting Times, and there's this supposedly this ancient Chinese curse about may you live in interesting times. The idea here is that to live in interesting times is a really bad thing. Now, this always bothered me. This bothered me a lot because I always thought that living in interesting times was a blessing. I couldn't imagine anything worse than living in boring times. So I always thought it was fascinating and disturbing that there should be a Chinese curse that you should live in interesting times. Of course, many of you will know I've had many fantastic, incredibly bright Chinese PhD students, and they're very quick to point out to me that this is not a Chinese curse at all. In fact, it was dreamt up by some Englishman, some English lord who was apparently depressed. And in fact, the Chinese have no such saying about interesting being a curse. And I'm pleased to hear that, because I think interesting is a blessing. And I want to convince you today that that we collectively, as a research community, live in extremely interesting times, and we've got an enormous amount of things to look out for. So a change of scene again. This, I took this photograph at dawn, looking west, so the sun's right at my back. The sun's just coming up. It's about 6 a.m. in Central Australia on a hike with my 14-year-old son in 2018. And our destination was that mountain in the distance. Maybe it looks close, but it's actually about 95 kilometers away. And we're going to hike there. And this photograph, to me, captures a lot of stuff. It captures the beauty. I think it's a beautiful landscape. It captures that beauty. It captures a sense, to me at least, of anticipation. The sun is rising. Who knows what's going to happen in front of us? It captures challenges. We've got that day we end up hiking. The hike in front of us was a very big one because there wasn't any water available, and there never is on this route. So you have to do a huge hit. So it's a 35-kilometer hike with a heavy pack in hot temperatures. So it's a very, very formidable hike. And so there's this anticipation of the challenge in front. But also there's this excitement of this challenge, and as I say, the beauty of it all. I think the beauty is breathtaking. So there's this interesting mix of emotions, and I think sometimes I see that as a bit of a metaphor for research. Excitement. There's also the hard work of doing that 35K hike. Anyone who's walked 35K with a heavy pack knows what I'm talking about. But research is often a lot like that. There's a lot of hard work. But it's very satisfying when you summit that mountain in the distance there. It's 1,300 meters, so it's not a small mountain. When you get to the top of that, you really feel a sense of achievement, and there's more to see there. So I feel like so what I would like you to come away from this talk with is the sense that challenges abound, that memory management has never been more relevant, and that there are enormous opportunities in front of us. So I'll just say it again, that memory management has never been more relevant, that challenges abound, and that there are opportunities in front of us. And that's the metaphor here. Okay, let me kick off with one of the heroes of our field, or one of my heroes at least, Barbara Liskov, and the Turing Award winner. And she, in her Turing Award speech, she spoke about the power of abstraction, which I think is a very important idea in memory management. But I also put her slide here because I think it's important, and you would have seen that if you've seen the abstract for my talk today. I put that there because I think it's fascinating. I think it's really interesting to reflect on our field and see how many of the biggest names in computer science made significant contributions to our little field. Why is that? Why is it that so many people like McCarthy, Dijkstra, Liskov, Steele, other huge names in computer science have contributed directly to memory management? And I'd say it's because memory management sits at a really interesting place in computer science. It sits between the hardware and programming languages. It contains rich problems, deep theoretical problems, as well as amazing challenges of engineering. So we've got very interesting performance concerns, which will consume the very best of our engineering abilities, as well as some really deep and interesting theoretical problems. So I think it's worth reflecting on that, and it's worth reflecting on the richness of the field that we're in. Also, I think that I find the talk that Barbara gave and the point about the power of abstraction an interesting one, because she also goes on to say that we need to relinquish complete control. And I always found that I found some dissonance with that claim that we need to relinquish complete control, because who wants to give up control, particularly when you're talking about the lower levels of the computer that you're trying to run upon, right? Giving up control always seems like a difficult thing. And I think the challenge for us as people who are dealing with layers of abstraction, whether it be through a garbage collector or through manual memory management or through whatever it might be, that this tension between delivering the right level of abstraction and giving up just what we need to give up in order to deliver the right abstractions without sacrificing performance. So that, I think, is a little bit of a backdrop to a lot of what many of us think, many of us do as we work in memory management. So it's perhaps a little bit rude of me to put this here, but this is a review Catherine McKinley and I got some years ago. Actually, it was for our IMIX paper. One reviewer wrote this. Essentially, this was the entire review. Isn't GC a bit retro? Now, two things. First of all, GC is definitely not retro. GC is actually everywhere. It's in your phone. it's in your browser, it's everywhere, right? It's not retro, it's very, very relevant. I'm going to tell you more about that in a minute. But also, ISMM is not just about GC, it's about memory management, and I'm going to talk about memory management in the broad, not just about GC. And so what I'm going to talk about right now is make an appeal to you that memory management is every bit as important as it's ever been. In fact, I'm going to claim that it's even more important today than it has been in the past. And I'll start off with a quote from a very recent paper from some colleagues at Google about memory. TC. This is about TC Malik and about how they worked with TC Malik to improve its performance on a huge scale. Okay, there are a couple of points in this quote that are relevant. First of all, the point that the memory wall, the so-called memory wall, that is the slowness of access to memory, still remains a serious problem, and that a very large number of cycles are wasted on this memory wall. And what they observed in their own study, and this is on a fleet-wide study at Google, so this is on a very, very large setting, mostly C++ programs, and they observe approximately 20% of cycles are stalled on TLB misses. Now, if you understand the scale of the Google fleet-wide system, 20% of all of that is absolutely enormous in dollar terms or by any economic measure, just in terms of how much silicon there is, how much energy is going into it, and so forth. So we're talking about a very large opportunity for impact. And they were actually, and what they report in their paper here is that they're able to reduce the number of TLB stalls and significantly reduce the amount of memory wasted due to fragmentation through the changes they made. One of the points they made in their paper and in their talk is that that historically the people working on TC Malik had focused very, very hard on optimizing the allocation sequence to ensure that it used as few cycles as possible, that it was very, very, very efficient. But in this work, they broke with that and instead focused on the locality and the impact of the decisions that were made at allocation time over the running of the program. And they actually took a hit in the actual allocation performance, but delivered a substantial overall win, which is, for some of you may not be surprising, but for many people, that's a slightly counterintuitive result. Bottom line is, the result here is a significant impact in dollar terms and energy terms and so forth across the Google fleet. So that's one point of motivation. So my point here is essentially that with something as humble, if you like, as a free list allocator, TC Malik, the impact for the opportunity to improve it and the impact that will have is absolutely enormous. Now I'm going to skip to a completely different point in terms of impact and the importance of memory management. And this is just a screen grab I took yesterday from one of my favorite Twitter feeds, which is Fish in a Barrel, which just talks about memory vulnerabilities. And you can see here, this is pretty typical. You can go here any day of the week and you'll see their latest, it's a bot, and you'll see their the latest memory vulnerabilities, and this is very representative. This is typically what you see. That is the majority, and often it's actually very close to 100% of the vulnerabilities that they disclose are due to memory unsafety. Memory unsafety remains one of the largest concerns, the most dominant concerns in security, and that, friends, it rests with us as a community. Memory safety is a critical part of what we should be caring about in the ISMM community, the memory management community. And this is not going to go away anytime soon. We've got a very real problem here and a lot of really interesting challenges in terms of how we deliver solutions without degrading performance in any significant way. So we've got some very serious challenges in front of us there. Here's a brief mention about one take on dealing with this. This is a paper from OSDI 3 years ago, using a new hardware extension on the ARM chips, which allows pointers to be authenticated. And this had been used previously to address control flow attacks. And what these authors here do is they extend it to deal with data-oriented attacks. And so they're talking about this thing called PA, which is pointer authentication in the ARM processor. and they used PA to build new defenses for a class of attacks, including data attacks as well as control flow attacks. So this is really exciting, and this is an example where a hardware vendor has innovated in ways that help us as people working in memory management deal with one of our really big concerns, which is memory safety. Unfortunately, some of you may have noticed this in the last few days. We now have, and we have a paper coming out. There's a paper coming up at ISCA in a couple of weeks, which presents the work that I just flashed on the screen there. Pac-Man, which is a novel attack that specifically attacks the pointer authentication mechanism that these other people were using to solve the other problem. So we've unraveled the very problem that we were just talking about. So you can see that second sentence in their abstract here. It says, our attack removes the primary barrier to conducting control flow hijacking attacks on the platform protected using the ARM pointer authentication. So this is a very live issue and hence not a very simple one. On the one hand, people are making great advances. On the other hand, we're finding out more vulnerabilities. So to those who might say that memory management or GC is a solved problem, wake up. There's a lot of problems. There's an enormous number of problems in front of us, and these are really interesting ones. Whether you'd be interested in security, or you'd be interested in performance analysis, or you'd be interested in computer architecture, or language design, any of these things, we've got a load of really interesting problems. Now, another point I wanted to make in terms of challenges is that of complexity. The richness and complexity of the architectures we sit upon, and the languages that we use, and the runtimes that support those languages. And here's a tweet just from a day or two ago from Dan Liu, and he's bemoaning people who trivialize the complexity of the memory hierarchy and brush aside suggestions that the memory hierarchies are something difficult to reason about. And you can go read the thread on Twitter if you want. But I'm totally with him. And I just want to briefly highlight a paper that we presented at ISMM last year. I'm just going to do this pretty quickly, but I'm using this to illustrate the point that the complexity of the context in which we're doing our work is substantial, and it makes things surprisingly difficult, surprisingly interesting, I think. Interesting in the best sense of the word. This paper here was led by Zhixian Kai, who's a PhD student working with me. In fact, right now he's doing an internship here at Google. And Mike Bond from Ohio State. And the paper was not about cache architecture at all. Sorry, the project was not about that. The paper actually is very much about that. But the project was a really, really exciting and interesting one that looked at seeing how we could use hardware transactional memory to efficiently implement concurrent garbage collection. Other people have done similar things, but we had a novel take on how we're going to do this. And Zhixian did fantastic work in implementing this, but he was flawed by a very surprising result. Things did not work the way they were supposed to work. Things did not, the whole approach in hardware transactional memory, for those of you who are not familiar with it, is that a number of read and write operations are essentially quarantined, if you like, if you want to think of it that way, are held up until a commit happens. And when the commit happens, they're acted upon in a way that looks atomic. So we're essentially producing a transaction. The key point, though, is this batching up of all this work is bounded. That's the key point. It's bounded. And it's mysterious as to exactly how it's bounded. And there's been a lot of work in the literature on studying how this is bounded. And here, this is a table from the paper, and you see all these papers here, all but the last one looking at the same architecture, all trying to measure the same thing. That is, how much capacity for writes and reads can the transactional memory take before you lose the transaction due to it exhausting its capacity, okay? And if you do that, you have to abort the transaction and try all over again. That's no good. So understanding this is crucial, because if you don't understand this, you can't design your algorithm. And remember, what we're trying to do in the first place, we're designing an interesting GC algorithm to do concurrent copying. And it depended entirely, the overall architecture of the algorithm depended on understanding this. But if we look at this, what we see, if you look closely at this table, you see orders of magnitude difference between the measured read and write capacities of the same architecture, the Haswell architecture. We're seeing a write capacity. If you look down there, we see on the third row, we see half of the L1 as a write capacity. And then if you look on the row right below it, we see someone saying that the actual write capacity is the L2. Okay, so we've got someone saying it's half the L1, another person saying the write capacity is the L2. And then if we look at the read capacity, we see it as being as low as 0.8 of the L1. And then we see in the very last row, we see it coming out as being roughly the size of the last level cache. These are enormously different results. And if you don't know the capacity of your architecture to within orders of magnitude, you've got a problem, right? So what's going on here? Well, the root of the problem is that it's very, very hard to reason about these proprietary implementations. And in fact, the core of the problem was not so much the HTM implementation, we kind of figured that out, but more about the cache architecture. And so many of you probably think you know how replacement policies work in a standard cache. We learned this at school, we learned this at grad school, how replacement policies work. You understand LRU, you understand even pseudo LRU. And those replacement policies are what's driving this problem, because essentially the way Intel implemented it was when you get a miss, a capacity miss, then your transaction will get blown up. So you need to be able to do your operations in a way that doesn't generate a capacity miss. How do you do that? Well, you need to understand how eviction works in a cache. That seems not too hard to figure out. Turns out it actually is. And the reason is that modern caches do not behave the way you learned at grad school. They don't use something like LRU or pseudo LRU, which is what you see in this illustration on the left, where things are essentially behaving in an LRU way. I'm not going to go into detail of the diagram, but I just want to illustrate very, very roughly here. What they're doing is using an algorithm like BRIP4, which is the one on the right there, which was developed to avoid streaming accesses from displacing the cache. And you can see visually, you can see the green on the left is displacing all the gray, and on the right it's not displacing the gray, which is good if you're trying to disrupt, you're trying to avoid streaming things from displacing your cache, but it's not good if you're trying to avoid capacity evictions, because capacity misses, because what ends up happening is the one on the right is generating capacity misses way sooner than you would expect. And the consequences of that, of course, were our whole algorithm fell to pieces, because we were implicitly premising our design on something on the left, and you can see the thing on the right is reality, and it's nothing like the thing on the left. So this is interesting, and why do I raise this in this context of this talk? I'm just trying to illustrate to you the complexity of the domain in which we're working, and that the complexity is increasing, and that this introduced more and more challenges, which I think are fascinating, and I think deserve a lot of attention, because if we can deal with these well, there's enormous opportunity. Now I'm going to change gears again, and again I'm going to talk about students' work, and in fact it's the same student as Zesian Kai, and this is a paper that we also did with Mike Bond, but also with Martin Mas, my colleague at Google, although we did the work before I joined Google, and this work was presented only about a month ago at ISPAS. I think this is quite interesting, because it helps us take a look at how garbage collectors, what the real cost of a garbage collector is. Now, up until now, pretty much everything I've said has been relevant to all forms of memory management. So in fact, I was explicitly focused on TC-Malloc for a bit there, and we're talking about all forms of memory management. Now I'm just going to talk specifically for a few moments about garbage collection and the cost of garbage collection. And so what we wanted to do is to want to understand how much garbage collectors cost. Zesian's PhD work is on looking at the possibility of accelerating in hardware, accelerating GC. And to motivate that, we wanted to understand how much was GC actually costing. We all had gut feelings about how much it costs, and probably you right now have a gut feeling about how much the cost is. And I think it might be helpful for yourselves, if you can, take a stab at thinking about what you think the cost of production garbage collectors are on a typical workload, on a workload, say like the Da Capo workloads, over a range of heap size, from a small heap to a very, very generous heap. Think about that. Think about the different GCs, the oldest GCs, like the old serial GC, which still ships, the parallel GC, G1, Shenandoah, ZGC, how much each of these GCs cost in that setting. I encourage you to think about that for a moment, and then I'll show you some interesting results. So the question Jacin's addressing here is GC really a solved problem? And how much does it cost? And how does that cost compare with the rest of the system? And here we've got a cartoonish picture of three garbage collectors. The bottom one is the no garbage collector, which doesn't collect any garbage, of course. That doesn't mean it's no cost, because in fact, the no GC, as you saw in the TC Malloc work, you can have TLB and locality issues if you don't do anything. And in the no GC case, we're doing nothing because we're just leaving everything in its where it falls, and we're not collecting any garbage. So these grey bars are cartoonishly representing the cost of these things in terms of the measured, perhaps the measured runtime. The metric we'll come to in a minute, but let's for the moment just think of this as the measured running time of these workloads. We've got a generational collector, and we've got a very simple one, say semi-space or mark sweep, something like that. Now the question is, how much is the GC costing in each of these? Well, most of you know, or many of you know, that there are some costs that are very easy to measure. So we can put a little instrumentation in that times the cost of a stop the world garbage collection, right? So we can see in the top one there, the yellow is representing the time when we're doing a stop the world garbage collection, and it has in this illustration here has two very big pauses where it does a lot of work. And then in the middle one there, we've got lots of smaller pauses for a generational garbage collector. And the bottom one, of course, we've got no pauses because it doesn't do any GC at all. It's just the mutator, albeit with perhaps pretty bad locality. But things are more nuanced than that. In fact, as you see here, hopefully you just noticed the color of that blue just changed to this murky yellowy blue. That's because there's actually GC costs bleed out into the mutator, because we have allocation, we have barriers, and we have indirect costs due to locality, all these things. So it's not as simple as simply extracting the cost of the application. And if you've got concurrent GC, things get even more interesting. So what we'd like to do, the methodology is really intuitively very, very simple. What we'd like to do is say, let's imagine what the ideal application cost is. The ideal application cost is the cost of running this application with a magical GC that does all the right things and costs nothing. So, of course, the magical GC does not, my watch is reminding me to relax. I'm enjoying this. I'm very excited to be talking about memory management. The magical GC does all the things a garbage collector should do, but it costs nothing. We don't have such a GC, of course. The question is, can we approximate such a GC? And the answer is, yeah, we can approximate it. And insofar as we can put an upper bound on that, we can put a lower bound on the cost on the overhead. All right, if we can measure this ideal application cost, or put an upper bound on the ideal application cost, then we know that then we can infer the overhead in terms of that. Okay, and the way we do this is we extract out the things that are easy to measure. Okay, so we leave on the floor those things that are not easy to measure, but we extract out the things that are easy to measure. Then we run our benchmark, and we call this distillation. So we distill out the things that are easy to measure. Then we run our workload, and we run our workload against a bunch of GCs, and we find the GC which has the lowest distilled cost. Okay, so the distilled cost is the cost after subtracting the things that are easy to measure. And we run our GC, and we take out the things that are easy to measure, and then we find the GC which delivers the lowest distilled cost, and we use that as an approximation to this ideal. Okay. So you can see that in the illustration there. And of course, it's always going to be higher than the ideal because we can't approach this magical GC. But the closer it gets, the better our approximation of the overhead is. Now, then what we do is we say, okay, let's look at the total execution time, or the total number of cycles, or the total energy, and we'll compare that with this minimum distilled application cost, and we'll say that the difference is the lower bound on the overhead. So there's the lower bound overhead there, and you can see these different GCs. So hopefully, so this is actually I think a very, very simple methodology, but it's new, and it has a number of very nice properties. You can apply this methodology to any language. It's not tied to any particular language like Java, and you can use any metric you like that makes sense, right? So you're not bound to using wall clock time. You can use cycles. You can use energy misses, whatever it might be. You can use whatever metric makes sense and apply the same methodology. And it's important to stress, it's not a case of just normalizing against something like no GC. What we do is we derive the minimum distill cost per benchmark. So for different benchmarks, it could be a different GC that delivers the lowest distill cost, and then we normalize against that minimum distill cost. This graph here shows us the performance across 17 Decabo benchmarks and a range of heap size. The x-axis is heap size relative to the minimal heap size. And it shows you the cost in terms of wall clock time for the 3 classic garbage collectors that ship with JDK 17. And you see the black line there is a serial GC, which is the oldest one. And not surprisingly, it performs the worst because it doesn't have any parallelism. And we're running on a parallel machine here. We're running on, what are we running on? A 16-way Coffee Lake machine. And so that's not very surprising. The black one would give us the worst wall clock time. And then you see the parallel one, which is giving us the best wall clock time until you get to the really small heaps. And then you see G1, which sits between them until you get to small heaps, and G1 breaks ahead. Okay, so this is the graph. I don't know whether this graph met your expectations about what the costs were. You see that in the limit, the cost varies from parallel to being about 4% to at worst, it's more than 40% up there on the left-hand end of that graph. So I don't know how that fits with your expectation. But let's do a couple more things here. This is just the beginning of our analysis. Let's now bring in the 2 new GCs that are shipping with OpenJDK or with the Oracle hotspot collector, hotspot runtime. And you see here Shenandoah and ZGC. If we look at wall clock time here, you see a very different thing. Now, Shenandoah and ZGC were designed to work with applications that run in very large heaps, but they also, as a consequence, perhaps, I'm not sure, but in reality, they require a lot of headroom. So if you run them without a lot of headroom and you don't have enough space, they actually take a long time to run because the GC has to do a lot of work. But even with a large amount of space, say 6x the heap, you can see that the time footprint is in the ballpark of nearly 25%. So it's substantially higher than what you see from these other simpler collectors. I think this is interesting, and I don't think this is particularly well understood. This graph here, suddenly we change gears, and we're no longer measuring wall clock time, but we're measuring cycles across all CPUs that are performing, that are running the application either through the GC or through a mutator. Now you see a different story again. Okay, the costs have raised. Notice also that serial is now the most efficient. Okay, so G1 and Parallel got their time performance by shifting load onto other cores. Okay, so if we look in terms of cycles, serial is pretty much where it was with respect to time, but the other 2 are suddenly looking more expensive because now we're accounting for the cost that they're imposing through their parallelism on other cores. And you get a different story. What I found a little bit disconcerting was to look at how these things go with respect to the age of the algorithms. And you can see a trend here, which I think should give us pause as a community. And we see that as time has gone on, our collectors, our runtimes have become more and more expensive, at least when we measure them in terms of cycles. Okay, so I think this is interesting, and I think this is something we should all be thinking about. Yeah, and this here puts those 2 things side by side, and you can see that if we don't measure the cycles, then we hide a lot of the cost. And I think that there's a real point here that we need to be careful about what we measure and how we measure it. Some of you may have seen this very silly poster. That's McCarthy there, and he's glaring at you because you're doing it completely wrong. I couldn't help thinking as I thought about the way we as a community been thinking about GC. I wondered what McCarthy would think about it, and maybe that's what his take would be. I don't know. It bears thinking about for a minute. But the more interesting question, that's just silly. But I think the more interesting question is how do we get here? And I want to make 3 points here. One is that there's a failure to translate. So there has been some really cool stuff. I'm going to glimpse at that in a minute. I'm going to show you a bunch of very cool work that our community collectively has done over 30 years. There's been a failure for academia in particular to translate into industrially credible frameworks. Now, I think that's really important. If you're under the gun in an industry, maintaining an interesting runtime, you cannot afford to be spending time on ideas that don't show any credibility with respect to the work that you're doing. So you've got more important, more pressing things to do. So academia needs to be able to demonstrate the credibility of its work in a way that is industrially relevant. And I think that's incredibly important. And I think that historically we as a community have not done a great job with that. And I think that's a two-way street. I think industry also needs to be open to that. there's been a failure to innovate. I think there's no question that as the pressures of working in production environments has led to monolithic collectors. There's some extraordinary examples out there in production today. Enormous garbage collectors written in a single large file, for example, and things like this. This is may look like an efficiency hack, but actually I'm going to argue that it's incredibly inefficient in the sense that by doing this, we block innovation. It's very, very hard to innovate when you're dealing with a monolith. Likewise, there's an enormous amount of pressure on anyone working in a production environment to break abstraction boundaries. And I'm going to claim that unless an abstraction boundary is mechanically enforced, it will be broken because it's just human nature to break abstraction boundaries. And as soon as you break abstraction boundaries, you get abstraction leakage. And when you have abstraction leakage, you will limit innovation. And the third point I want to make is our failure to measure. I think methodological insight is not valued highly enough by our community, and I don't just mean ISMM, I just mean our community more broadly. Methodological insight, I think, is incredibly important, and without methodological insight, we don't notice where we're costing. And if you don't know what you're costing, you won't be addressing the problem, and you won't be, and worse still, you'll be leading people astray because you will be misleading people about where the costs are. Not intentionally, of course, but just as an artifact of not having a measure that actually accurately measures both the cost and, really importantly, as we showed in those previous slides, the opportunity cost. Okay, if you're burning up a resource and you're not counting for the fact that that resource could have been used for something else, then you're masking an opportunity cost and you're sweeping it under the rug. Okay, so hopefully at this point, I've convinced you that, one, memory management is as important as ever. It's critical to a large number of systems on your laptop, on the servers in the cloud, on your phone, everywhere. Memory management, whether it be automatic memory management in the form of GC or manual memory management, it's incredibly important. And we've got major concerns that confronting us, both with respect to performance, with respect to space efficiency, with respect to security. And I also want to point out with respect to space efficiency, there's a myth that space is cheap. I can assure you that memory is not cheap. And I've spoken to people who deal with the cost at scale for these acquisitions, and memory is a very real concern. The cost of memory is a very real concern. We cannot discount space when we think about memory management algorithms. Again, whether it be manual memory management or GC, space matters a lot. And you saw that in those slides from the TC Malik paper, that the defragmentation made a big impact in their space consumption, which had very direct cost savings. So that's a little reflection on what I've said so far. Now what I want to do is to reflect very, very briefly on ISMM, 30 years of ISMM and IWMM. And what I did is I just spent an hour or so going through the proceedings of each of these conferences over 30 years. It's 30 years, folks. So, you know, congratulations, community. We've 30 years since our first workshop, IWMM in St. Malo in 1992. In those 30 years, we've covered an enormous amount of ground. I'm just going to show a few papers here, just a tiny sampling of what's out there, and invite you, as you sit and just watch a few of these things go fly by your screen, to reflect upon them and reflect upon maybe some trends that you're seeing or not seeing, or where the impact is. So I want to call out just one or two of them out loud. This one here is very noteworthy. This appeared in the very first proceedings, and it's a landmark study. If you haven't read this, please go and take a look at it. It's an amazing account of garbage collection techniques from Paul Wilson at the University of Texas in the very first proceedings. Then for those of you who understand region-based garbage collection, this is kind of the progenitor to a huge amount of that work. This is the MOS algorithm from Rick and Elliot. The next IWMM, Paul Wilson and his students produced this amazing overview, a survey of dynamic storage allocation. And again, if you have not seen this, you definitely need to take a look. It's an amazing piece of work and a real testament to Paul and his students and his colleagues. Erlang, this is this work from Harlequin on now pre-tendering Tim Harris, thinking about how heap objects are connected, real-time Java, scope memory regions, static analysis in this case, Oops. Mostly lock-free Malik, Dave Dyson, Alex Garthwaite. Dave Detlefs again here. This is the original G1 paper with Christine and Steve and Tony. Transactional memory allocator. Interesting work here from Intel. Phil, Daniel, Erez, and Bjorn talking about low pause garbage collection. This work here, these people went on and did a really interesting, or some of these people went on and did really interesting work in JavaScript. Hans has been doing amazing work for a long time with C++ and memory management. Most of you will know that. He's done a huge amount of work in other areas as well, but his mark on that area is incredible. Real-time garbage collection, again, in that case, it was hardware. This is one of the most cited papers in the history of ISMM. Very interesting paper on safety for C. And NUMA C4, another very important piece of work here. This is one of the, today, still one of the most important low pause garbage collectors in the literature. A great piece of work here from folks at Berkeley. Completely crazy. Can you do GC in a GPU? And this is one of my favorite papers, just simply because of the audacity of it. Scala and Java, pointer analysis, hardware transactional memory, and doing garbage collection using hardware transactional memory. Really interesting work in JavaScript from the V8 team. And this one here from my own group, but I still think this is a great piece of work. I think it's an interesting piece of work, really interesting, using Rust as a language for doing high-performance GC implementation. Then hybrid memory systems, very interesting. More and more interesting work here. Oh, here, working in a completely different language environment, which I think is very, very interesting. So not just looking at the more tired Java and so forth. TensorFlow here. And persistent memory, and then finally another paper from the folks at Google looking at a framework for automatically generating fundamental memory operations, which I think is really interesting. I think generating frameworks that help us think about how we measure performance is very, very interesting. So that's just a glimpse at a handful of papers covering a span of time. What doesn't show through there, which I think is perhaps worth us reflecting on, is I think I'm going to stick my neck out here and say that I think Java caused us a big problem, because I think that there was, over time, when I reflected on the ISMM proceedings, there was a lot more work in the earlier ones on diverse languages and diverse systems, and things became a little bit more homogeneous and perhaps not quite as strong as people focused more and more on Java GC. And I think there was a sense in which, oh, GC for Java is a solved problem. There's not much to be done here. It's game over. And I think that was a big, to the extent that that happened, that was a big mistake. Okay, so that was a little reflection. Hopefully at this point, I've made the point to you that GC's, not GC, memory management is as important as ever. And that there are a huge number of challenges in front of us. And we've done some great work in the past, and a lot of very diverse work. Now I'm going to look forward, like I did when I took this photograph. That was the hike I was about to do. Look forward to what our opportunities are. And I think there are amazing opportunities in front of us. I want to start with this one here. And this is, that's a die photograph of the Zen 3. The reason why I put this here is one of my amazing undergrad students did a research project earlier this year, and looking at barrier costs, because you can never study that too much. And she found, she had this very disturbing result that took quite a lot of her time, or a huge amount of her time, and a lot of my time too, and other people in the group, trying to understand why it was that for a few workloads, when she added a write barrier to the workload, the performance improved. Okay, of course, for most workloads, the performance degraded. And in fact, on nearly every architecture, all workloads performance degraded slightly when you added a write barrier. But on the Zen 3, there were 4 workloads for which performance improved. And Xalan was one where it was statistically noticeable. And this is completely repeatable. Okay, so what's going on here? How is it that by injecting a conditional and a bunch of other instructions into every pointer store, performance will consistently, statistically, significantly improve? And after a huge amount of work, I can tell you I have no idea. And I think this is interesting because I think it reflects on the complexity of our modern processor cores. They're incredibly difficult to reason about. And that might sound like a very negative thing to say, but I actually think this is very exciting. I think it's exciting because I think there's a lot to be understood. And importantly, barriers are a really important, powerful tool for people who are designing GCs to think creatively about a GC design. And if we can find that in our modern processes, these barriers cost nothing, or by some fluke of magic actually speed things up, then we should think more fearlessly about how barriers can allow us to do more creative work in a GC design. This is the Apple's latest system on a chip design. This is the M2. I just put this here because it was announced just the other day, and it reflects the growing heterogeneity, I suppose, and diversity and complexity of modern silicon, the opportunity for acceleration, the changing of the memory hierarchy, memory getting closer to the cores temporally in some sense, and memory bandwidth going up. There's so much change going on. This was just from a few days ago. There's an enormous amount of change going on, and this change directly impacts the way we think about memory management. Completely different topic here. This is a die shot of Intel's 3D X-Point, which has become known as the product called Optane. I think this is interesting because this completely changes the way we think about memory density, about memory performance, and of course about persistence. And so there's a whole lot of opportunities there for us to think about using this for persistent storage, or simply using this as high density storage as part of our regular heap, whether it be with respect to explicit memory management or GC. A lot of really interesting challenges there. I know a bunch of people in the community have already started looking at that. This one here is Samsung's PIM product, HBM PIM. And for those of you who are not familiar with PIM, PIM is essentially an old idea that dates back decades, but the idea is essentially that you can put a processor in the memory fabric, allowing a great deal of parallelism and very high memory bandwidth for things that are not compute intensive. And GC is an obvious opportunity there, and a number of people in the community have been looking at this. So I think that's a really fascinating line of work. I don't have any deep insights about how we're going to do that. I know a number of people who are working on it, and I think that's really, really exciting. This is a paper here by my colleague Martin Mas. And the real point I want to make here is that there's a real opportunity for us to think about how we might be able to apply ML to systems problems. And Martin talks about a taxonomy here of including anomaly detection, forecasting, extrapolation, discovery, and optimization. And many of those are applicable to the challenges that face us in memory management. So applying ML to memory management, and of course, memory management ideas may help us do ML better as well. But applying ML to memory management is a really interesting and open problem. And I know people like Elliot published recently on using ML to predict GC, when to do GCs, for example, reacted to. And I guess my reaction is this, and that is performance is not the enemy of security. I think complexity is the enemy of security, and it's also the enemy of performance. Complexity is our enemy, not performance, okay? And I think this is relevant because I want to now talk about opportunities with respect to software engineering. And I'm going to invoke Fred Brooks here and talk about what he said about conceptual integrity. And I think this is so important. And I'm going to rant again about the problem with monolithic garbage collection and implementations and the problems with abstraction leakage. I think these things here are completely understandable. I totally understand how we got there. But I think that they really stand in the way of innovation, and they really stand in the way of security, and they really stand in the way of performance ultimately. Yes, optimizing some monolithic code base may take you to a local minima, but it's very, very unlikely to get you to a new global minima, or to the global minima. It's not going to work you in that direction at all. You're very likely to get trapped in a local minima when you have these, when you don't think really radically about software engineering. So I'm going to suggest to you there's an invitation to think radically about software engineering. And if software engineering is your thing, I think there's a wide open field for thinking about that in the context of memory management. I want to briefly mention MMTK. I'm super excited about this. In fact, only just before I started this talk, I saw an announcement from the Rust Foundation that someone I'm working with, Joanna, had just received a fellowship to work with us and the MMTK group in getting PyPy ported to MMTK. She's already started that work, and I've been working with her and Carl Bolt, and she's made great progress in getting MMTK working with PyPy, and that's why you see the PyPy logo there. But we've been working with Ruby, Haskell, OpenJDK, Julia, PyPy, V8, and of course originally with JXRVM, which still has MMTK bindings there. I'm mentioning this to you because I think this is exciting. Why is this so exciting? I said a few slides ago that I was concerned about the dominance of Java in a lot of the memory management work, both overall, that is, the GC is dominated over the manual memory management, but also I think that people have said, oh, GC is a solved problem with respect to Java, or not a solved problem with respect to Java, but implicitly ignoring all the other language systems that have that depend on GC or have interesting memory management. So I'm very optimistic that by doing this, we can re-energize memory management research in these very interesting domains. And I found it absolutely fascinating to see the progress of MMTK ports in these different languages and the very interesting needs that each of these languages has. There are a bunch of other interesting languages, including Coca from the MSR group, and they had a really great paper at PLDI last year for garbage-free reference counting. So take a look at that. And also older languages like Erlang and OCaml, which have taken at a language level, and Coca have taken at a language level a very different approach to memory management. And finally, Rust. I want to mention Rust again. We've built our whole system on Rust, but also I think Rust itself has some interesting memory management challenges. It's taken a very interesting approach to memory management. I think offers us a lot of opportunity. I want to, the last point I want to make is methodology. I already showed you this slide here, but I just want to reinforce the need for us to value as a community the importance of methodology as an underpinning for everything we do, and that we need to think creatively. And I think that we need to reward people who think creatively about methodology. And with that, I'm going to finish up. I want to recap by saying, I don't think there's ever been a time where memory management has been more relevant. It affects more people today than it ever has before. It affects people through what's in their pocket, in their phone, through the way they communicate with the server, through the way they interact in a browser. It very directly impacts people everywhere, whether it be automatic memory management or manual memory management. And I think that there are an enormous number of very interesting challenges out there, and they're multi-intersectional, intersecting software engineering, computer architecture, programming language design, and so many other things. There are vast opportunities, like in this picture here. There's a great hike in front of us, a great challenge in front of us, and I'm really excited by it. Hopefully you can see that I'm energized by this, and I'm very interested to take questions and to hear what any of you might want to ask, or how any of you might react to this. So thank you once again. I've been really honored to be able to give this talk. Thank you.
Thanks a lot, Steve. What a ride! Lots of memories, lots of very interesting work. A quick shout out to everybody on Slack. Please feel free to ask questions. I can redirect them to Steve here. In the interest of time, let me ask a question. So, my team is working on client side garbage collectors. So it's working on garbage collectors for phones, for browsers, and so on. Are we lost with not understanding all the cache hierarchies and architectures for all the systems we're actually shipping our systems on? Or is there some hope?
You know, I think you know me well enough, Michael, to know I'm the eternal optimist. I think there's loads of hope. I'm certainly not remotely depressed by it. I'm just excited by it. I think that what we're going to see, and I think you know this from your own experience, that things don't work uniformly. They might be correct uniformly, because we have ways of ensuring that, but their performance may vary wildly. And I think when we see a new a new product being released, a new processor coming out, whether it be coming out from Google or from Apple or from someone else, or Samsung, we don't know how the systems we've built on the client side are going to perform on those, you know, and the impact of these innovations are going to have on our systems. So I think it's just a really interesting open question. And I think also, I want to make the meta point, having just made this transition from academia to industry, there are things that people in industry do not have the luxury of pursuing that are very exciting, that academia very much can do, and vice versa. Okay, I've heard people say, oh, I can't get into this field because industry dominates it, or whatever, thinking there's some sort of dichotomy. I think there's an incredibly powerful synergy between academic work and industrial work. And so it may be that the pressures that are placed upon industrial teams like Michael's team are ones that actually create enormous space for people in academia. So for the PhD students out there, there's just so much interesting stuff here for you to work on if you're interested. And Michael's just pointed to a bunch of them. Understanding memory hierarchies on these different devices is and how they impact on the performance of the thing running on your phone, I think is really, really interesting.
Thanks for giving us some hope here. There is a question on Slack. Yatin Manekar, sorry if I did not pronounce it correctly. Steve, in your talk, you mentioned recent architectural developments and how memory management might be able to take advantage of them. To flip the idea a bit, what can architects like myself do to help the memory management community? Thanks.
Oh, that's a great question. Thank you, Yatin. Look, I think there are a couple of things you can do. One thing that's been the curse of academic architecture research, you know, I've been on the edges of the architecture community for a long, long time, and that is the historical dominance of the spec and the way we evaluate architectural work. I think it's really important that we think more broadly, and that and I do very much understand how much more difficult it is to evaluate dynamic or just-in-time compiled languages in an architectural setting. But I think that as architects, it's really important to include studies of things like languages like JavaScript and Java and more diverse languages in the study. So that's one way, that is to evaluate in those contexts. But I also think that there are people who you can collaborate with who will be very interested to talk to you from this community, from the memory management community, who will be very interested to talk to you about opportunities for optimization, whether they be for GC or whether they be for memory safety in a language like C++, or whether they be for something else. I think there's just an enormous number of opportunities there. So hopefully that may have answered your question a little, Yatin. I think it's a great question, though. I'm happy to talk more about that too. There's a question. I can see Slack now. I can see Chen's question. And Chen's asking, in addition to Michael's initial question, with multi-cores, the cache hierarchy, especially the lower levels, is shared, so the available cache changes depending on what programs are running together. Absolutely. And you know, you saw that little example I gave from Zusian's work with hyper-transactional memory and us understanding the behavior of the last level cache on the modern Intel processors is kind of mind-blowing. There's some incredible work being done. And the way we cracked that nut, incidentally, was through reading through some reverse engineering. The reverse engineering was the only way to understand that. And then once we reverse engineered what was going on through a huge amount of help from a research group in Europe, microops.org, I think is their website. Once we've done that, looking back at the papers that have been published by people like Norm Juppy describing those algorithms which seem to have been implemented in these things. So yeah, understanding the behavior of those caches and understanding the interactions between the programs that we might be running and those other programs is incredibly important. And the reality is, yes, in most systems we don't run in isolation. So understanding the impact of those other ones is very important. Any other questions?
Let me ask one more. Different direction this time. So I know you've been working with MMTK on different language runtimes at this point.
Yep.
What would you wish for? Like I know V8 is historically very hard to work with, right? If we would build a new runtime, what would you wish for from an academic memory management perspective?
Oh, I don't think V8's a problem at all. I mean, it's very highly tuned. It's very large and very complex. It has all those things. But in terms of what I'd wish for from an academic context is a modular interface and well-defined and machine-checked abstraction boundary. I think those things are crucial. And I think there's been some fantastic work. I think Eric Osterland at Oracle did amazing work with the Java runtime in abstracting those out about 4 or 5 years ago. That led to a lot of great work, and that helped us enormously when we ported MMTK there. So I would just say that machine-checked abstraction boundaries and that avoid abstraction leakage would be the #1 thing I'd be asking for in any industrial runtime. Can we have the list of the ISMM papers Steve showed, says Chen. You know, Chen, the way I got most of those is I went to the ACM Digital Library, and if you click on the event, if you go through all the ISMMs, I went to DBLP, got all the ISMMs and IWMMs, and then if you click on the digital library version, you can see all of the papers and how many downloads they got and how many citations they got, and that basically guided my selection of that list. But I'm very, very happy to provide the list to you if you like. But basically, I just grabbed the ones that seem to have been most referenced over the years in each of these places. That's how they got there. Now, I think Michael. Oh, yes, the question.
No, that's really ingenious. So just list the papers by the reference count.
Essentially, not exactly. I took some liberties, but that's approximately how I got them.
Thanks.
All right, now Michael knows that I'm at Google, and I'm going to kick you out of this room on the dot of the hour because because the way room scheduling works here. So I think I need to finish up.
All right, then let's thank Steve once again, virtually, remotely, in person. Thanks a lot, Steve. Was a pleasure having you here. And
no
please, please, people, stop. Don't stop. Continue discussing things in chat and maybe find space in Gather. Right.
Yep, I'll be available if people want to ask me questions, but I'll be offline for a moment or two while I exit this room I'm in. But thank you all for having me, and it was honestly a real honor to be able to present this work. So thank you.
All right. Let me quickly bring up. And thanks for making this work, right? I realize hybrid conferences are not easy. Technology is not always with us, as we just heard. So there is issues, and there will be issues in future, and we'll just have to make it work somehow, right? In that sense, but I also want to provide a feedback link here. So please give us feedback. We will make sure that feedback is heard. And accommodated as much as we can, right? So the ISMN generally follows PLDI and PLDI guidelines, which I think makes a lot of sense in that context. But if there is room for us to grow there and change things that didn't work well, we should definitely do them, right? And we'll also investigate in how we can better maybe accommodate industry talks and people, right? That may not have the liberty of contributing full papers all the time. In that sense, I think that's it from my side. Please continue on discussing and collaborating, right? Slack is open 24/7. It's just for some of us, it's getting late, and so we'll not stick around. But for everybody else, right? I know Australia just got up, right? So there's plenty of time to continue. All right. Thanks a lot, and having said that, bye.